Hey everyone, today I want to cover a non-uniform charge density problem, which can sometimes be a little bit tricky for students to understand because it often involves, doing some extra integrals and it can sometimes be a little bit overwhelming. So hopefully today's example will be helpful with understanding how to deal with these problems. And so our goal is to figure out how the electric field of the system varies as a function of r. In other words, as a function of the distance from the center of our sphere. Okay, so to do that, let's consider Gauss's law. So this is going to be critical. The reason why we can use Gauss's law is because we have spherical symmetry, which means that, so I'm going to write Gauss's law. This is the charge enclosed over epsilon naught. What this is saying is that if we have, for example, cylindrical or spherical symmetry, this integral over here becomes really simple. Specifically, when we have a spherical case, what we can say is that the electric field at the border of our Gaussian surface, so you can imagine our Gaussian surface being a sphere that starts at the very center and sort of expands as we ask it what radius we want to find the electric field at. Since we know that this is spherical in symmetry, or spherical in sort of charge density, it means that no matter at what point you look at within the surface of this Gaussian sphere, the electric field magnitude will be the same in strength. That's just a fancy way of saying that we can pull out the electric field from this integral and just be left with the integral of dA. And dA, by definition, is just a small patch of area within the sphere. And so if we just add up all those little patches of area, we're just going to be left with the whole area, which means that I'll just write Q enclosed here. We can write E times the area of the sphere, which is 4 pi r squared. And this is still equal to Q enclosed over epsilon naught, which means that we can solve for the electric field and have Q enclosed over, and in this case we get 4 pi r squared epsilon naught. And in fact, we know that this is going to have a spherically symmetric electric field, so we can just write r hat as our vector. And so it would be really nice if this was the answer, and it technically is, but we are not, we don't know what Q enclosed is. We need to figure out what that is. And that's going to be the main challenge in this problem. And so what we can do for now is, let's just grab this equation, and let's just put it over here. And when we figure out Q enclosed as a function of r, then we can just plug it in and get the answer. So great, we have that done. Now let's actually figure out what the charge enclosed is. And so to do this, we're going to have to consider the volume charge density. And so in this problem, we're told that the volume charge density is a function. It varies with the radius, r. And so what it's saying here is that as the radius increases, so the farther away we get from the center, the amount of charge per volume is going to increase. It's going to increase quadratically, to be specific. And so that is going to add some complexity, but that's okay. We're going to deal with it. We're also told that c is a positive constant, so we're actually going to have to solve for it to, solve this problem. And we're also told that the total amount of charge in the system is q. And so if we were to solve the case for the electric field where little r is greater than big R, so if I'm asking for the field outside of the sphere itself, then this would be a pretty simple problem, because it would say that the charge enclosed is just equal to the total amount of charge that I'm enclosing, which in this case is just the total charge, which would just be Q. And so our electric field would just be essentially like a point charge. It would just be Q over 4 pi r squared epsilon naught r hat, which is essentially this equation, but just with Q in it. So that works great when we're outside the sphere. But when we're inside, it gets a little bit more complicated. And so that's what we're going to have to solve for. And so the way we're going to think about this is in terms of the definition of charge enclosed mathematically. So charge enclosed can be defined as just a sum of charge, a sum of small amounts of charge within some volume. So essentially what I'm saying here is if you grab some volume, for example, this sphere over here, and I add up all the little bits of charge inside, if I add all those up, that's going to be my charge enclosed. And so that's what I'm going to do. I'm going to solve this integral. But the problem with this integral is that it's not really clear how you would do this. And so we're going to have to transform this dq infinitesimal value into some variable that we can actually integrate over. Ideally r, because that's our radial distance. And so if we have a function of r, then we can actually integrate over the sphere. And so this is how we're going to do it. This is how we're going to do it. So we're going to say that dq, our little bit of charge, is going to be equal to our charge density, or volume charge density, times dv. And why does this work? Essentially what this is saying is, well, volume charge density by definition has units of coulombs, so charge, over meters cubed, volume. And so if I multiply this by some volume, which has units of meters cubed, then this will just give me charge, because the units will just give me charge. And so what we're saying here is, okay, if we have some charge density, if I multiply it by some volume, then I'm just going to get a little bit of charge. Perfect. Great. So now I guess we can go back here and we can say, okay, we have some integral. We have rho now, which we can replace with our function, and we have dv. But now how do we, solve this, right? dv isn't really easy to integrate over by itself. And so we're going to have to write dv in terms of r. And in this case, we have a sphere. So this actually isn't too bad. And the way that I would think about it is, think about the volume of a sphere. It's given by 4/3 pi r cubed. You can think about it in terms of like what dv would be as just differentiating both sides. So we can say if I differentiate the right hand side in terms with respect to r, I'm going to get 4/3 times 3, which comes from the cubed, pi r squared, squared. And of course the 3's cancel, and so we're left with 4 pi r squared. And we can also include a dr here if we're being precise, which we should be. So I'm going to include a dr here. And since we've differentiated the right, we can differentiate the left and keep it as dv. In other words, to clean this up, what we're left with is dv is equal to 4 pi r squared dr. And we can see that it still maintains units of volume because we have an r squared here, meters squared, and dr, which is meters. So overall, we get meters cubed. Great. So now we can replace our dq expression with rho, and instead of dv, we'll write 4 pi r squared dr. Perfect. So this means that we can replace our integral over here and write dq like this. The integral of rho times 4 pi r squared dr. And in this case, we're interested in integrating from 0. And since we want it as a function of r, we can just write r here. The more mathematically inclined of you, I guess, will be a little bit upset that I'm writing r here. And maybe we can fix that by just adding some primes here. This is just mathematical notation. And so, okay, so we have this expression. All is good. But if we want to really be precise, we should probably solve for what c is. And so what we're going to do is we're going to use this integral and we're going to say, okay, I know that the total charge in the system is q, big Q. And so what I'm going to say is, okay, big Q is going to be equal to the same integral that I wrote before, but instead of my bounds being from 0 to little r, it's going to be 0 to big R. Because what this is saying is, if I integrate over the whole sphere, I better get the total charge. And so what I can say is, okay, now I'm going to replace rho with the actual expression, cr squared. Now I'm going to write the rest, 4 pi. In this case, I'll keep it as regular r. Great, we can simplify this a little bit more, so let's pull out some of the constants. In this case, we have 4 pi c integral from 0 to r to the 4th dr. So this is the integral that we're solving, so let's actually do it. So here we're going to have 4 pi c. We're going to evaluate r to the 4th, so in this case we use the power rule, we get r to the 5th over 5, 0 to r, and if we evaluate this, we're going to get 4 pi c over 5 big R to the 5th. Great. So it looks a little bit ugly, but that's fine. And we know that this has to be equal to the total charge. And so what we can do is we can solve for what C is. So we can multiply by 5, divide by R, so we can do all of this. We get C is equal to 5 over 4. We're doing math here, pi, and then I'll include the R to the 5th here. And then, of course, Q. So we have 5Q over 4 pi R to the 5th is equal to C. Awesome, so let's just grab this equation. Let's just put it down here. Let's make it all nice and tidy. And great, we've just solved for what C is. So this is really useful because now what we can do is we can go back to our function for charge enclosed and we can actually solve this integral using C. And so let's rewrite this integral here with everything that we know. So we'll call this 0 to R. And here I'll be even more explicit. I'll write Q enclosed as a function of R. And then rho is going to be C, which we just found out here is 5Q over 4 pi R to the 5th. This is actually big R to the 5th. And, R squared stays there times 4 pi R squared dr. And in this case, again, we can add the primes if you want. So I'll add them to be more precise. Perfect. So now let's continue solving the question. So here we can see that these 4 pi's cancel, so that's useful. Let's pull out any other constants that we see. So in this case, we have 5. I think, Q is also a constant. And I think that's all the constants. So I'll just bring them down. The 4 pi's cancel, which is nice. Oh, we also have big R to the 5th. That's also a constant. And so inside, we're just going to be left with these R prime squareds. So let's just include those. This is going to become R prime to the 4th, dr prime. And this is very similar to what we just solved. And so let's go through it anyway, just to be precise. So we have this. And now when we integrate this, we're evaluating R prime to the 5th over 5 from 0 to R. And of course, this gives us 5Q over 4/5, or 4 to the 5, but we have a 5 here as well, so these cancel, times R, and yeah, R to the 5th, there we go. So if we want to be very clean, we can say this is equal to Q times R to the 5th over big R to the 5th. And this is great, because what we can say is, okay, when little r is equal to big R, in other words, when we've reached the edge of this sphere, then the answer better be big Q, the total charge. And we can see that that's the case, because when little r is big R, this becomes big R to the 5th over big R to the 5th, those cancel and we get Q. So this is how we can check our answer. Great, so we've done a bunch of work so far, and we're almost done. Because now we can erase all of this work, and we can just gently move this result all the way over here. We can put back our equal signs, and perfect. We now have the Q enclosed. So I'll make some space over here. And what we can do now is we can bring our electric field function, and we can say, okay, we now know Q enclosed. Let's just put it in and see what happens. So we're going to have the electric field is equal to, and in this case, Q enclosed. I'm going to write it out first. So we're going to have Q R to the 5th over big R to the 5th times 1 over 4 pi little r squared epsilon naught, and then r hat. Great, so let's see if anything cancels. Well, let's write it out a little bit more neatly. We can see that this r to the 5th and this r squared can cancel out. And so we can get Q on the top, and we can get 4 pi, and in this case, we're going to get r cubed at the top. And then here, we're going to get epsilon naught, and then r to the 5th, and r hat. And this is our answer. This function tells us what the electric field is for r between 0 and big R. And so this is useful, and we can check that it's right in a couple ways. For example, we can set little r equal to big R, so this is a pretty useful tip. If we set those equal to each other, we have big R here, the r cubed and the r to the fifth, well, this is going to cancel out, this will become a squared, and we can see that it becomes a point charge, which is what we saw before when we were checking the outside field. So that's reassuring. We can also see that this works out in terms of units. I guess we already showed it because, we have meters to the power of 3 and meters to the power of 5. Well, this effectively just gives me meters squared down here, which is the form that we would expect for our answer. And so I hope this was helpful. I think the crucial parts is just with the math when you're sort of talking about what dq is equal to and how we can express this in terms of dr. But yeah, this is it. I hope you guys appreciated this. Feel free to ask any questions, and I hope this helps. Bye-bye.